Welcome back to Machine Organization and Programming. This is the final lecture from week 8. We're in the middle third of the course here where we're talking about assembly language. So the first third was about C. Then we're looking at one level lower with assembly and how it's going to connect to the machine hardware. And the final third of the class is special topics. So in this week, we took a look at some of the bit operations, how data is stored in memory, how to do binary arithmetic. We finished up the C section with file. And now we're going to be diving into assembly language instructions. This is found in section 3.1 to 3.5 of the computer systems book. And again, this is one of those places where the book goes very deep. And what I want to do is provide an introduction that makes the book easy to read. So you can go, oh yeah, this is complicated, but Mike talked about it in lecture. I do understand it. That's my goal here. And again, there are excellent practice problems for all of these topics at the end of each section. I highly recommend you take a look at those. They provide the answers. They're excellent. I'm going to be basing my quiz questions and my exam questions from those questions. So those are the best possible practice you can get for this section. All right, so without further ado, let's go ahead and just dive into this assembly lecture. All right, so the next third of the course, the middle third, is going to be about assembly language programming. So I just want to back up a little bit and quick review. This is some of this content from the very first lecture. I tweaked these slides with a little more detail, but at the very first lecture I was asking what happens when we run a program. And the first step is we compile that. We've got our source code over here on the left in the green where we're writing in C. That goes to the compiler. We're using GCC for this course, and that produces a binary executable. And then when we actually run the program on disk, I've got my source code stored here in a text file, plain text, and I've got the binary file with all of the ones and zeros that the machine needs to run. Now, the source code here, definitely human readable. We actually write that ourselves. When we run this code, we're going to be loading the binary from the disk into memory. And this is going to have 4 different sections when we get to the memory. And we'll talk about this in a lot more detail coming up. We have the code section. This is going to be, so I wrote some C code here, when in fact these would all be ones and zeros. And these are just instructions that the processor over here is going to use to decide how to execute each of the commands. There's a data section. This is going to be our global variables. So we saw a lot of that available in the project 2, where all of the strings were global variables. They would all be stashed in data. The heap is going to be our dynamically allocated memory. Anything we use malloc for is going to appear on the heap. And then the runtime stack. And here I've drawn main with A, B, so I cut off execution right there after A and B, so we don't know what C is yet. I left that blank. All right, so a little bit more about how the CPU is going to operate. First thing it's going to do is fetch each of these binary instructions. That's going to have a number of pieces to it in the instruction. It's going to be a command that tells it what to do, like over here. This third line down is an addition command. So it's going to say, okay, this one's addition. I'm going to be adding 2 things together. What am I adding? So those will be the next 2 pieces. And then where does that go? So anyway, the fetching the instruction just grabs it and brings it into memory. Then there's a decoding step that says, this is adding. Here's all the pieces when I break down the instruction into all the components. And then it's going to execute that instruction. All right, and then this just repeats. It goes back and gets the very next. So one of the challenges we run into when looking at designing a computer architecture and how this actually works on the inside with the hardware is that CPU is extremely fast. It can operate at something like 1 billion operations per second. That's 1 nanosecond per operation for those of you guys who love math. And one of the problems is to bring memory, like if I want to grab this A value here, move it to the processor to be added, happens at about 100 times more slowly. So the CPU can do 100 operations in the time it takes to just grab one value. So the secret, the way we mitigate the fact that the memory is so much slower, is we're actually going to put memory on board the processor. Now there's not very much. There we go. We just have a couple of registers available to us. They've got weird names. They start with a %, EAX, EBX, ECX. These are the general purpose registers. This is where we're going to move the values over here before we do the math with them. We also have an instruction pointer or program counter, IP or PC. I just used IP for this abbreviation. And this is going to be just a pointer to the next instruction that it's about to operate on. So over here, I've got my C code. Now, C code is going to get broken down into a number of steps to perform all of these operations. So this would actually not be pointed to C code. It's pointed to some binary, and it's going to be the first step in what happens to compute this sum. And I've got just a quick demo here. This line right here is actually going to get translated into 4 separate pieces. First, it's going to move some location in memory, like this one right here at address 100, into one of the registers. So %EAX right here is one of the registers. It'll copy that value over here. And then it's going to move the other operand, the B, from that addition we're doing. In step 2, it's going to copy that into a different register. And then it's going to add. The way this is read is it's going to take the contents of that register, add it to EAB, that register, and then it's going to store the result in that second register. So this is the source register, destination register for all of these instructions. And then we'll see that we just need to move that back into memory. So it's going to copy the result of the computation after we've done the addition back into C over here. So like I was saying, each one of these move instructions is very slow, and we don't have very many of these general purpose registers. But if we're doing something like iterating through a loop and just incrementing a value by 1 every single time through the loop, if we can keep those values in the processor's registers, those operations are going to happen at 1 nanosecond each, 1 billion per second. So it's going to be very quick to go through all of those things. If we have to go back and forth to memory, like we're doing here in this operations, and much slower. All right, now if we go back and just real quick review the build process. When I have my source code and it goes through the compilation process, there's 4 steps that happen. The first one is the preprocessor is just going to take all of the compiler directives and go ahead and, for like an include statement, just copy and paste that file. And for a define, it's going to create a compiler variable, and copy and paste that in throughout the code. So those sorts of things. That's going to give us this pre-processed source file. The compiler proper is the one that's going to produce the assembly code. And this is the complicated, really hard part. We teach an entire class about this. It's called compilers. Anyway, this is the one that's going to take our C code, break it down into all of those individual steps to produce the assembly code file. So the source code over here, definitely human readable. We wrote that ourselves. Assembly code is, I'm going to go with barely human readable. People actually used to write this by hand for very specialized applications where performance is critical. You'll still see people writing this by hand. But by and large, the reason we're studying this is because we want to be able to look into our code and see what's happening here before we get to the executable over here. And maybe we can write slightly more efficient code if we understand what happens under the hood as these assembly instructions are created. So that's the idea. We're looking at improving performance by understanding what's going on inside. And for the most part, most of these C code instructions are translated into many lines of assembly code. And then the assembly code is basically translated 1 line into 1 binary instruction. So this is very close to the machine level code. It's just a lookup table that figures out how to translate the assembly instructions into machine code for the most part. All right, just like there's lots of different kinds of programming languages out there that all end up giving you the power to write computer code that does stuff, there's several different kinds of assembly languages out there. We're going to be focused on Intel's x86, but there's a number of other assembly that have been designed for other architectures like ARM and Spark, and actually lots of others. Just advance here. Yeah, so the Intel x86 assembly language was designed for this series of processors developed by Intel. The 8086, the 8186, the 8286, the Pentium. So if you look, they all end in 86. And the rest of these are all sort of just a prefix. So they're going to abbreviate that prefix with X. The Pentium came about as the 5th generation of the 8186, 286. There's 386, 486. My very first computer back in like 1993, I believe, was a Pentium. So I did have one of these. They're been around for a long time. Okay. We also find that there's actually two different versions of x86 out there. One developed by AT&T for use with the Unix system, and the other one developed by Intel, used with MS-DOS and Windows. These are very similar. One of the major differences is whether the source comes first and then the destination, or the destination first and then the source. And we're going to be focusing on this one right here, the AT&T version developed for Unix. All right, if we zoom in a little more deeply and take a look at the actual registers in the CPU, what we're going to find is that we have 6 general purpose registers, these first 6 right here. They all begin with a %E, all the registers do. The E stands for extended. Percent tells us it's a register. All right, and now if you take a look at these carefully, we have the A register, the C register, and the D register for the first 3. And then B. These are divided into like 3 parts. So we have they're all 32 bits, numbered from 0 to 31. The A register here was 16 bits. They're the lower 16 bits of the EAX. And I can address each of these individually. This much in the box right here is just the %AX. Okay. If I want to get the whole thing, I need the extended version, the EAX, which is what we'll almost always use. And for backward compatibility, they also included the ability to address the lower 8 bits and the higher 8 bits of the bottom half of this. So, all right. Big picture, EAX is all 32. AX is the bottom 16 if I just want half of that. And I can divide this into 2 parts also, and I can address the AH and the AL. H for high, L for low. And that's true for all of these, the first 4, the A, B, C, and D. Then ESI and EDI are just another 2 registers. We'll use them. We'll talk about the specific uses for those, but in general, you can think of them as general purpose registers for most things. There are certain assembly instructions that require very specific registers to be used. Division is an example of that. We'll talk about that in a little bit. And then there are 2 very special registers that should only be used in a very particular way, and they're available for managing the stack. So this would be the stack pointer. This is going to tell us where on the stack we're currently looking at memory, and the frame pointer. This is going to be when you add a new function call, it adds a new frame to the stack. This is going to point to that. So we'll talk about those. My advice right now is don't mess with those. All right, for doing regular computations and stuff. So during the rest of today's lecture, I'm going to be talking about 4 very specific topics. The first one, transferring data to a register. And then we'll be talking about how to do arithmetic operations with those. Just addition, subtraction, multiplication, and division. Just the basic ones. And then we'll look at how to connect the registers on the CPU to the memory and actually bring things in and move the data into the memory so we can access it and use it for computations. And then we'll take a look at bitwise operations at the assembly level. So I'm going to jump over into a text editor. Actually, I'm just going to go use Vim, and that way I can walk through and develop each of these assembly instructions one at a time, and not just blast you guys with PowerPoint slide after PowerPoint slide. All right, I thought I could do just a slightly better job explaining what's going on with these registers. So back in the mid-70s, what we found is that the 8080 Intel processor had 1 byte or 8-bit registers. And so they named the first one A, the second one B. So if we just took a look at the A register, this is what we'd see in the 8080 processor. Then when we moved up to the 8086, that 86 family of processors to start up, we found that these were 16-bit machines. So I had 6, 7, 8, 1, 2, 3, 4, 5. More pieces to them. So this is now the AX register. Get my language right. And it's divided into 2 pieces. This is the higher order bits, so AH, and then let me do it with brackets so it makes a little more sense. The lower order bits, AL. And I can address either one of these, even on the modern processors. So this A was retained for backward compatibility. This would have been the equivalent of let's do it kind of like that. the low order bits from the 8080 processor. Okay, and then as technology advanced, we're now looking at 32-bit registers. So that's why we've been compiling with this M32 option. All of the assembly we're looking at is for x86 32-bit. So they've extended it. So now we have EAX registers. And this added an extra 16 bits at the front. So there we go, there's 16 more. And then we've got the AH, 1, 2, 3, 5, 6, 7, 8, and 1, 2, 3, the AL section of it. So this is the extended version. So, and I don't have the power to address these by themselves without some tricks. But the AH and the AL and the entire thing, EAX, are all available to me. One sec. I should probably put some percents in. Let me go back and add those. There we go. All the names of registers begin with a percent. So wanted to add those to be clear. All right. So my first topic from that list that I was putting up there a moment ago is data transfer. This is going to be how do we move data into registers. And the command for that, the syntax is just MOV. And then I'm going to have my source of the data and the destination. So the destination is going to be register if I'm moving data to the processor. Okay, so as an example, if I want to store the number 27 in the EAX register, it's just going to look like this. I'm just going to say move. Because it's an immediate operand, I'm just using a literal number. I'm going to prefix that with the $sign. Okay, so all of the immediate numbers are going to be they start with a $sign anytime I want to use a number, and that can be in decimal or hexadecimal. So I'll give you an example of that in a second. Move, and all the registers, begin with that percent. So EAX if I want to move 27, and I can do this with hex values too. So an immediate, there we go, immediate 0x100. Store that in EBX, another register. Okay, so one of the little tricks that can be a little confusing is that assembly can accept either decimal values or hexadecimal and will frequently use both, sometimes even in the same expression. Typo there. Okay, got it. All right. Now there's a number of variants. We'll almost never see the MOV without one of these suffixes. So the variants are going to be things like MOVL, and that's going to be for like a move long, which is going to be all of the it stands for long word, which is all, let's see, 1 2 3 4 5 6 4 bytes of the register length, all 32 bits. So example of, we can move number 30 into register EBX. Oops, typo. And this is going to be L stands for long word, which is 4 bytes. There we go. All right, I feel good about that. That makes sense. Okay, we have move W, which is and we're going to stick a number 30 in. In this case, it's only 2 bytes long, so %BX. Now, this doesn't make a lot of sense because when we're talking about a 32-bit machine, we would talk about a word size being the size of an integer, the most common size. We would expect this to be 32 bits. But remember, those original 8086 machines were 16-bit machines, and so sort of the wording, the labeling on all these assembly commands stuck with that 16-bit machine label. So when I move a word, W here is going to stand for word, and this is only going to be 2 bytes when we're referring to assembly instructions, even though that doesn't make sense because modern machines are now 32-bit or 64-bit for modern, like really modern ones. 32 for the class. Okay, so that's move W, and then we also have move B, and that's going to stick the number 30 in just the lower part. I forgot my percent. And this is just going to be moving 1 byte. So I hope this makes sense. Move L is the one we'll almost always see. These will be under special circumstances if you're doing something special. But yeah. All right, just a quick note. If I do something like move L and I want to stick all ones in the bottom, this will be 8 bits. This actually sets the rest of those bits to 0. Sets upper, let's see, 32 minus 8 is 24 bits to 0. Bottom 8 to 1. Okay, so it is going to clear out the rest of those. But something like this, where I'm moving just 1 bit, the 30 into the bottom 8 bits, does not change the rest of those. It just leaves them alone. It doesn't do any more work than it needs to. So most of these the other instructions were just retained for backward compatibility with things that had already been written long ago. Alright, next up I want to talk about the arithmetic instructions. Addition, subtraction, and integer multiplication all follow almost the exact same syntax. So, for example, addition, I have add. It's going to have one of these suffixes, L, W, or B. So add L in this case, I'm going to use the full register for everything I do from now on, with a few exceptions. So add L, and this is just going to be source and destination. Okay, so basically this is going to be destination is where we store the result, D plus S. No punctuation right there. Subtraction works the same way. Command is SUB, and then L for the long word, source, destination. And again, destination is where the result goes. And we're just subtracting, subtract. Yep, so it's the destination, take away the source is going to be what's stored. So for addition, it didn't matter which order these were. For subtraction, this is important. It's the destination where we're taking away from. Okay, and then for multiplication, we have integer multiplication, so imul, and then for long words, and again, source, destination, and D times S. So it looks just like that. All right, I'll do some examples of these in just a second, but I want to talk about division first. All right, first up, just a little bit of vocabulary as we start taking a look at division. If I'm looking at a problem like 7 divided by 2, 7 is going to be known as the dividend. It's the number we're dividing, and 2 is the divisor. So 7 will be in the numerator, that's the dividend. 2 is the denominator, so the divisor. Now, x86 permits us to do 64-bit dividends, and they do that by letting us put the dividend into 2 registers. So they're going to use EDX and EAX. I'm just double checking my notes to make sure I don't screw up. So this is going to be where I put the number that I want on the numerator, the dividend. And so this is going to be a full 8 bytes in this order. So EDX will be the high order 4 bytes and EAX will be the low order 4 bytes. So it'll for the dividend. And then when we do the integer division, we'll put the number, the divisor, somewhere else. So for example, divisor goes, well, somewhere else. And then when the results are stored, it's going to compute both the quotient and the remainder. And when it does that, so we'll have the quotient being delivered to, don't screw up Mike, EAX, and the remainder is going to be stored in the EDX. So when I do the division, I'm going to put my data into those 8 bytes up here, and then the result of the division overwrites them. So this is going to look something like this. Where's my notes? All right, found it. This is going to look something like this. I'm going to have integer division with long words, and then all I need to just specify is where I'm storing my denominator, divisor. So easy X. Alright guys, at this point I think it's probably best to just get some practice to dive right in and try and write some of these little commands yourself, just to like get the feel for this. So there's a worksheet available on Canvas go ahead and download that. It was developed by Ramsey when he first taught this class back, I believe, in 2012. I got the 2017 version of this worksheet. I really love it. It's got a great summary of everything we're going to be talking about at the beginning. And then go ahead and just pause the video and try and do questions 1, 2, and 3. Just invest a little time, figure if, they're a little like a puzzle. See if you can figure it out, and then come back and I'll show you the answer. All right, so question 1 asks us to move 1 into, just a quick note right there, into the register EAX, and then we're going to add 10 to that and put the result back into EAX. So to start off with, move, I want to move L. I'm going to put the immediate value 1 into the destination EAX. Now, if I want to add a number to it, that number has to be in a register. So I need to move, let's see, in this case I want a 10. So in the $10. And I need to put it somewhere other than EAX. So in that case, I'm going to go with EBX. There we go. And then I need to do the addition. So we'll add, again, these are all long words. So I want to add EBX to the destination EAX. So, all right, very good. Let me format this a little better and pull up the next one. All right, the next question asks us to evaluate this mathematical expression, 3 plus 6 times 2, and order of operations will matter here. We'll need to take care of that ourselves, but using only one register. I know I implied up here in my previous example I needed to use EBX to store the 10. That's not true. I can take immediate values and just operate with them the same way I can. So we'll demo that real quick. We're going to do this in exactly 3 instructions. So the first thing we need to do is we'll be using the EAX register. So I need to get started by putting a number in there. So in this case, I'm going to use the 6. So move a 6, let's see here, immediate 6 into EAX. So the next thing we're going to do is multiply that by the 2. So the order of operations are preserved. So that's integer multiplication for long words. And I need an immediate 2, and I want this to go into that destination, EAX. So the destination is always a register, EAX. So that'll take the 6 times 2. And then the next thing I need to do is add the, let's see, what was it? 3. Add 3 to it. So we'll do add L, immediate 3, and EAX again. Okay, there we go. All right, let me type in the problem for problem 3, and then we'll go through it step by step. All right, guys, I got this typed in. So I'm looking at problem 3. It's just a bunch of assembly instructions, and the question is asking me what computation is this actually performing. So let's take a look at this. As I start at the top, I see I've got a bunch of move data into registers, and then I'm going to be dividing by whatever's in EBX. So let's take a look at this. If you remember how division works, we've got 2 registers that are going to represent the numerator. We've got EDX, and let me do it this way, and then EAX. And this is going to give us a full 64 bits of information that we can use for the numerator. So in this case, we've moved 0 into EDX, so I'm just going to make a note that that's 0. And we moved 7 into EAX, so this is going to represent 32 bits of zeros, and then lots of zeros, and then some ones. Okay, and then we're going to put 3 into EBX. So I'm just going to keep track of these others. I'm going to use, we've got a bunch of divisions, so I'm going to use EDX and EAX up here in my code just as notes. And I'm going to keep track of EBX down here contains 3 at present. So what we're doing is we're taking essentially 7 divided by 3 right there. And if you remember, that's going to store the remainder and the quotient in these 2 things up here. So EDX gets the remainder, and let's see, 7 divided by 3, remainder is 1, and the other register, EAX, gets the quotient, which in this case 7 divided by 3 goes in twice, 2. Let's put the word quotient in here too. So there we go, part way done. After that, we move some more data around. So it looks like we're going to copy EAX, which is right up here. It's got 2 in it, into ECX. So ECX now contains 2. All right, following that, we've got some more moving and then another division. So we're going to move 0 back into EDX to cancel. Right now it's got a 1 in there. If we were to fail to do that, we'd be dividing by some really ginormous number with the 1 in the 32nd bit position. And then we're going to put a 9 in the EAX, the lower 32-bit. So let me just make a copy of this piece right here. Let's see, after we do all that moving, it's going to look like this. So we put a 0 here, we put a 9 right here. There we go, like that. We put a 2 into EBX this time. So that's where we're putting our denominator, or the divisor. And then we do this division. So this is essentially, let's see, 9 divided by 2. And that's equal to, well, do it this way. I've got my remainder and quotient pieces. That was not copy command. Why? Paste that in. Okay, so when I take 9 divided by 2, the remainder is still 1. That's stored in an EDX register. And 9 divided by 2 looks like that's going to give me a quotient of 4. There we go. From there, we're going to take EDX, that's the remainder, and store that in EAX. All right, from here on, I'm done with my division, so I'm just going to have EAX down here. Remainder was 1, and from there, we're going to add ECX, which was the result of my first computation, to EAX. So EX is going to become 3. And in the end, the computation that I did was 7 interdivision by 3 plus, let's see, 9 modulus 2. Let me double check my notes, make sure I said that correctly and not backwards. 7 divided by 3, 9 modulus 2. Yep, that looks good to me. All right, next section. All right, so next topic is accessing memory. We've got 5 major ways that we'll be able to access different parts of memory. Very useful for things like if I just want direct access to a memory spot, or if I want to look at a particular index in an array, or if I've got a struct. So that's why we've got all these different modes. The first one is known as absolute addressing. And this is just where I'm going to just go to a memory address and read what's there. So I've got some sample memory there in my example. And if I want to go read the value that's at memory address 1000, all I need to do, here we'll move it into a register, is give it that address. No $, just a straight number means go get that stuff from memory, that use that memory address. And then we'll store it in EAX, just to complete the command. I need to highlight real quick that if I leave off the 0x and move that into EAX, I'm no longer addressing in hexadecimal. It's going to automatically convert this to hex for me. Here we go. And actually reads low memory location. I just figured this out. Let me check my notes. 0x 38E. 3E8. There we go. That's correct. All right, so instead of the 1000 I thought I was getting, where I've got my 74 stored, this is going to go read somewhere else that I had not intended. So it's important to be careful here and make sure that when you put in the number. All right, so 2 things. Use hex and no $sign to get memory. If you want just a regular number, you need the $sign to indicate that it's a literal number. Okay, the next mode is called indirect addressing. Indirect addressing. And this is where we're going to be using the register to hold the memory address that we want to go retrieve. So in this case, let's move a literal address, so in this case 1000, into a register. Put in EAX, and then if I want to go to that memory address, we'll go to 1000 and grab the 74. I need to put the register in parentheses. So that's just the clue that says this is a pointer, it's got an address in there, go dereference it, grab the 74 and store that in, I don't know, EBX. All right? So also pretty straightforward. Use the parentheses to represent like a dereferenced pointer. So this is indirect. It's not going to actually take the value that's in EAX. It's going to go to that memory location and do it. So parentheses mean indirect. Okay, so next up, number 3 is the base plus displacement increment addressing. I can spell, I really can. There we go. Typing in all caps without the caps lock key, I'm pretty good at, but I'm not perfect. Okay, so here's the idea. We'll start with an example for this one. If I'm moving, this is going to have 8 times percent EAX. We'll store that in EBX. So what this is going to do is it's just going to take the memory address. So it's going to use the 1000. Every time I see parentheses, this means it's indirect. So this is still an indirect address, but it's going to increment it by this number here. So it's going to go grab this base value, increment it by 8. So we'll have OX 1000, because that's what I just stored up here in EAX. And then we're going to add to it 8. And I'm going to switch this to hex right away, because when we do addition, they'll be in the same. And 8 in hex is the same as 8 in decimal. So that's going to work just fine. This is going to give us OX 1008. And this will store the 42 in register EBX. So I think this is also pretty straightforward. You can think of this as a way to index into index into an array. So if I know that my base value, the very 0 address of the array is there, and I want element like 2 integers down, I just need to go 8 addresses down further in memory. So add 8 to it to get to the, 4 would be the index 1, 8 would be index 2, if they were 4-byte integers in an array. All right, this next mode is called indexed addressing. And I was trying to think of a good example that would demonstrate why we would ever want something this complicated. For example, let's take a look at this struct here. I've got a struct point. It's got 2 pieces of data. The first is an integer, and then a character array that I'm using to label it with. Y is probably not the best label because you think it points at X and Y. Just go with it. Oh, good Lord, look what I did here. I switched those. All right, we got to fix this. And Carol, let's change this. We can fix that right now. We'll call it name. And we'll just go ahead and add another point Y. There we go. Now it's a point. It's got a name. Looks much better. Okay. Now if we want to access the third character of the name, I want to get to right there, we can use this indexed addressing mode. Basically, we're going to assume that the base of the address is stored in the first operand right there, EAX, and we're going to assume that index 2 is stored in EBX. So what I need to do is recognize when I store a point like this, it's going to reserve 4 bytes for the X, so that this will be where the very first base address points to, is that X. Another 4 bytes for the Y right here, and then beyond that I've got 42 bytes reserved for this name. Okay, so time out, let me fix this too. No, fix. Good Lord, I cannot type today. There we go. So the way this works is it's just going to take the sum of these 3 things. So this is going to take, here, the base address plus the index. So this base address is my EAX. It's the first thing right there. The EBX is my index, and that's going to be the 2 in this case. So I would need to move 2 into EBX to make this work. And then this is going to be the offset. Let's see. They've got a better name for it. Oh, they call it an immediate value. So I'm actually we'll put this first. So we'll go with immediate in this case. So that 8 would represent these, the 8 bytes for the 4 for X and 4 for Y to shift us down to get to the start of this array. So base address is where the point is stored. Immediate is going to get us shifted to the start of the character array, and then the index would have a 2 to get us to that second character. All right, so I know this is getting complicated, Just wanted to like go through an example. If you need to, pause the video, go play that back again, and then rejoin me right here. All right, last one, guys. This is known as scaled index addressing. It's the most general. And in fact, all the rest of these are just sort of special cases of what we have going on right here. The way this works is I've got 4 parameters I'm going to put in to get to a particular address. There's an immediate value that's just added to the base, and then there's an index times a scale factor. So this is frequently used to address access into arrays. So I'll have an index, and then if it's an array of integers, my scale will be 4. If it's an array of characters, this will be 1. If it's an array of shorts, that'll be a 2. My choices, I can only use the values 1, 2, 4, and 8 for this scaling factor to represent the values of the sizes of different primitives. So for example, if I go back to this struct example and I've got my character array, to do the same thing here, I would be moving 8 to get past the X and Y to jump to the character array. And then my base here would be a register. The index also must be a register. So EBX here. In this case, this would be my index value. So I would have 2 to get to the 0, 1, 2. And then I'd have a scaling factor. And here the scale must be an integer 1, 2, 4, or 8 to represent the size of this array. So this is a much more common, you'll see this sort of address mode used to index into integer arrays more commonly than this. You'd use the special shortcut version without the 1 if it's just a character array. No reason you couldn't do it this way. Very common. And in fact, you can leave out any of these pieces and they'll just be assumed to be 0. For example, if the base of my array is actually at 0 for some reason, which I'm not allowed to access, I can write this like this and just put the comma in, leave out that value, and it's good to go. Basically I can leave out any one of these pieces and it's still going to be just fine. And that's where I get these like shortcuts, is by leaving out the extra data that's here in the scaled index addressing. All right, so next up, we're going to jump back over to that worksheet. There's a whole bunch of examples to give us some practice with addressing. Let's go ahead and do that now. So just pause the video, go see if you can figure those out, and then come back and I'll go through all of the solutions to talk about how we get there. And if you made any mistakes, you can sort of learn from them. All right, guys, I got problem 4 copied in here, ready to go. So we're looking at a bunch of addresses in memory. I've got 4 of them here, 100 to 10C, and some values stored in there. And then I've got 3 registers I'll be using for these examples, and these are the values currently stored in those registers. And then I just want to figure out what number do I get when I use each of these different addressing modes. Okay, so if we start off with %EAX, that just says just go grab the value that's in EAX. So I'm going to go get 0, 100. Oh, excuse me. My voice is really scratchy today. All right, I'm better. Grabbed a drink. Things are good to go. Okay, so next up, if I'm looking at OX104 with no prefix, this just means go get whatever is in address 104. So in that case, I look up here. 104 has 0xAB. OXAB. There we go. The $sign here means this is an immediate value. So the value it's going to use is exactly like it says, 108. Okay. When I see parentheses, anytime I see parentheses in anything, that means this is like indirect addressing. So like I can treat EAX as over a pointer. So I'm going to go to EAX, find out that that contains the address where I really want to go look stuff up. And I can see that gets me to the FF. All right. Come on, Mike. There we go. All right, next up. This is going to be, again, indexed addressing, or indirect addressing, because I've got the parentheses. So I'm going to go and figure out the address where I need to go look something up. This is going to be insert. No, insert. So the address is going to be 4 plus whatever is in EAX, and that's OX100. So I convert 4 to hex, I add them together, and the address I get is OX104. So in the end, the value I'm going to put in there is the AB. Yep. Okay. So then, looking at a slightly more complicated version, This is going to be my immediate value, the base, and the index. So when I figure out what this is, insert. I'm going to be looking at 9 plus whatever's in the EAX, and that is 100 plus, and then whatever's in EDX, which is 3. So when I add all of those together, 9 plus 3 is going to be C. So it's 9, 10, 11, 12, A, B, C. Yep. And 10C. So 10C. When I go there, I see that I have 11. All right. Starting to get a little more complicated now. Okay. But this is another example. This is exactly the same thing, except that I've got to do a little more math now. So I take 260 plus OX. Let's see. ECX contains 01, OX 1, and EDX contains 3. So that's going to be 4 in hex plus whatever 260 is. So let's see here. 260 divided by 16 is Now guys, it's getting late in the day for me. 260 in hex is 104. All right, so we've got 104 here plus 1 plus 3. So this is going to give me 108. So in the end, the value that I'm going to get is the 0x13. There we go. All right, and then this is finally we're getting to the scaled stuff. All right, so this is going to be OX, so I need the address. OX FC. This is going to be plus, this base value is not here, so that'll just be 0. We'll just leave it out. And then I've got whatever is in ECX right there, 01. OX, we'll just do it that way. This is going to be times 4. So, all right, let's see here. That's going to be 4 total. OXFC is going to be OXFC DEF0. So that's going to be 100. And when I go and grab 100, that contains FF. All right, looking good. Finally, last one here. So this is another one of those scaled index addressing, except now I don't have the immediate value, so that'll just be left off. And we're going to go with EAX. Let's see, EX is 100. We're going to add EDX, which is 3 times 4. All right, so that's 12. 12 is C, so we've got OX10C, which means that I'm going to be grabbing the value OX11. All right, let me see. Yeah, there's a ton of really great practice problems in our textbook. They did an excellent job of just supplying example after example of problems like these. So I highly encourage you guys, as you read those sections from the textbook, to go through and do all of these kinds of examples. They also make great inspiration for exam questions. So I've got one more topic left for today. I'm going to go prepare some material, and I'll be right back. All right. I feel like this video is getting to be quite long. I've been sitting here for several hours now recording little pieces of this at a time. So I want to just wrap this up real quick, and then I'll do the editing, and then we'll find out just how long it really is. But the last topic is the Bitwise Operations. Okay, here's the idea. In C, we had a bunch of different Bitwise operations. There was AND, we had OR, there was the exclusive OR, the NOT, we had left shift and right shift. I love the way Vim actually assumes that I'm making brackets when I'm just, typing some text in. All right, so the commands that we're going to use to do these operations. For AND, it's just the word AND. I'm going to put that suffix on to indicate what kind of data I'm working with, so long here, long words, and then source and destination. This is going to be stored in D. Okay, pretty straightforward, I think. The OR operator, keyword OR, and then the suffix for whatever kind of data I'm working with, source and destination again. Exclusive OR, this is just going to be XOR, kind of data I'm working with, source and destination. All right, the not is a unary operator. Keyword is just not, followed by what kind of data I'm working with, and then this is just going to be the destination. It's just stored right in the exact same position. All right, now these are the ones that always confuse me, the shifting operators. So I'm going to spend a little more time and maybe talk a little more slowly. So we've got two different kinds of shifting. We've got arithmetic shifting and we have logical shifting. So the first one here, if I'm doing the left shift, so that's going to be shift arithmetic left, shift arithmetic left, and then the kind of data, so SALL, is going to shift by k bits and store in the destination D. So that's going to be D gets DK, something like that, if I were to write it in C. And this one is going to be the arithmetic left shift. Okay? And remember, left shifting, it doesn't really matter, we just always push zeros in. But they do include the logical left shift. So shift, logical, left. And else for the type of data. So shift, logical shift, left, type of data. Okay, and again, this is just going to be KD, okay, comma D, and this is going to store just like that. It's going to store the value of D shifted by D in the same memory location. Okay, and again, that's just going to be, when we do a left shift, we're just going to be shifting in zeros. So those two are equivalent. Okay, next up, we have the shift, arithmetic, right for long data. Okay, same deal for the parameters that this takes, the operands. This is going to do D, destination gets D, right shifted by K. Okay, just for completeness. Arithmetic right shift. Spell carefully, Mike. Okay, and this is the one that's going to fill with the most significant bit. This is the one we would see for signed data in C. Okay, and then let's see here. I'm gonna actually shorten this up a little bit so that it all fits in one line and looks good for you guys. So next up, last one, we have a shift, logical, right for whatever type of data. In this case, long words. KD. Let me just fill this in to complete my little table here. Logical right shift, and the logical one is the one that's going to just fill in with zeros for unsigned data. A little dash right there. Okay, that's all I want to do is just introduce those. Go check out the textbook, take a look at their examples, get some practice there using these. We'll see these in the future. And I think that I'm going to just wrap it up right here, go do some video editing, and then see if I can get this released pretty quickly. All right, have a great day, everybody.